Hello and welcome to Doc Clay's Chemistry Lessons. Today we're going to be looking at the AQA A-Level Chemistry and A-Level Practicals and the practical activities 7 through to 12. So, previously we've looked at the practical skills from the AS level, and if you want to see those you can click on the link that's coming up now. But today we're going to be recording the 6 additional practical techniques for AQA A-Level Chemistry in this Year 13 course. And these are looking at those which are numbered 7 through to 12. So in the last video tutorial I gave about practical activities, you could see what was happening in the first 6, 1 through to 6, and again if you want to click on the link that's coming up about now, you can find out about those here. Today then we're going to be looking at measuring the rates of reaction, measuring the EMF of an electrochemical cell, investigating how pH changes when a weak acid reacts with a strong base, the preparation of organic substances, how to carry out simple test tube reactions, and the separation of species by thin layer chromatography. First up then, we're going to look at measuring the rates of reaction, number 7, a continuous method, and follow the rate of reaction basically as it's occurring. And there are 4 main ways that we can measure the rate of reaction. We can do it here by looking at our gas volumes that we've seen before, where we measure the volume of gas as the temperature proceeds. We can also measure how the mass of a reaction changes. So perhaps we've got a solid in our beaker and the mass decreases as the reaction occurs. We might also measure the pH of a reaction, and here we've got a pH meter in a conical flask to measure the pH. Or finally, we might measure the change in colour of a reaction with time, and in order to do that we use something called the colorimeter. So measuring the rates of reaction, we're basically going to follow the rate of reaction as it's occurring, and what we're going to have to do is whatever data we collect, we've somehow got to convert that measurement into a concentration so that we can measure it as a function of time. We've got an example here of some data where we've got the concentration of reactant, which is changing, and that's plotted on our y-axis, and we got time here in minutes in this case along the bottom axis, the x-axis. And we can measure here then the rate is the change in reactant concentration divided by the time. We can measure the rate then, we can describe as the gradient of this graph. The gradient of the graph we can determine by the change in y, and that is then divided by the change in x. So to work out the gradient of our reaction, we choose 2 points on our graph, and then we work out what the change in y and the change in x is. So for our example here, the change in y we work out to be 0.14, take away 0.50, giving us a value of 0.36 moles per decimeter cube because we've got a concentration, and our change in x is the difference between the starts and the end. So we've got 15, take away 2.5 minutes. Normally we're dealing with seconds. This graph happens to be minutes. And we get a value of 12.5. The difference between these two values, we divide 0.36 over 12, giving us a rate of reaction here of minus 0.029 moles per decimeter to the minus 3, minutes to the minus 1. Apologies there, I've missed out the half a minute in my calculation. This method is all well and good when we've got a straight line, but tends to fall down when we've no longer got a straight line, but our rate of reaction actually changes with time. So in this instance, what we have to do is we have to take, let's say we're trying to find the rate of reaction at 3 minutes. We have to take the tangent to that line by placing a ruler on the curve that just touches the line and drawing a straight line, what we call a tangent to that curve. Once we've done that, we draw our line, and once again our gradient becomes the rate of reaction, and we can calculate what the change in y again divided by the change in x is for this tangent to work out the gradient. So again, here at 3 minutes, we've got a tangent that's just touching the line, and our change in y this time we can calculate to be 0.46, take away 0.22, and our change in x being 5.0 minus 1.4, and so our gradient we can calculate here to be 0.24 divided by 3.6, again giving us a gradient of 0.067 moles per decimeter minus 3 per minute. Now, the next way we need to know about measuring the rate of reaction is by the initial rate method, or the clock reactions. We can do this by calculating, like we have done there with our continuous rate method, but we just take the tangent to the curve at time 0 and once again work out the gradient by working out the change in y by the change in x. What this does is it gives us the rate at the start of the reaction. Once we calculated the initial rate for a given reaction, we then need to repeat that whole experiment another time, but we change the initial concentration of one of our reactants. Once again, we then calculate, we plot, and we work out the rate at the initial rate of reaction by doing the tangent at time 0. We do this for several experiments, changing the condition or the concentration of one of our reactions. We calculate all the initial rates from these graphs, and then we compare the rate of reaction when we change initial concentrations to give us the order of the reaction. And we covered that in a previous lecture on rates of reactions. Now, a simpler method of doing this is called the iodine clock reaction. These are simpler because we no longer have to plot numerous graphs, and we make some simplifications in this experiment. The clock reaction easily estimates the initial rate of reaction and it is taken as the time taken for a set amount of product to be formed. Now, this is normally done by doing it as an observable endpoint, such as a colour change, where we observe the concentration of the reaction don't change significantly over time, period of the clock reaction. We have a reaction where the temperature remains constant, and also when the endpoint is seen, the reaction has not proceeded too far. In other words, we're actually seeing the initial rate of the reaction. Actual clock reaction looks at the reaction of hydrogen peroxide with iodide ions to make iodine. To see the iodine form, we add starch, and when that has happened, we see the change from blue to black. So the starch and iodine form a blue-black solution. Now, in order to ensure that we get to the same endpoint each time, we add a certain amount of thiosulfate. We keep the concentration of thiosulfate the same, constant, and this then consumes a given amount of iodine, preventing the solution turning black. So our thiosulfate concentration is constant and consumes a certain amount of iodine, ensuring that we always get to the same point for the initial rate of reaction. We measure the time taken to do this, and then we repeat the experiment by changing the hydrogen peroxide concentration, and then we can repeat the experiment again by changing the iodide concentration. Since the concentration of thiosulfate remains constant and we always generating the same amount of iodine, we are always measuring the initial rate of reaction. The only thing that we have to do between reactions is to ensure that our thiosulfate concentration remains constant and that we keep the total volume of the solution the same by adding water to ensure that concentrations are changing, but the total volume is the same in all the other experiments. Now, number 8 practical activity then is measuring the EMF of an electrochemical cell. In an electrochemical cell, you have to do a few key things in order to measure the voltage between two half cells. The first thing that is required is you need to ensure that you have drawn, if you're asked to, electrodes. And these electrodes require two things. They have to be able to conduct electricity, obviously, otherwise if they can't pass electrons, they're no use. And they need to be either part of the half cell. So in this case, we've got zinc in a zinc solution and copper in a copper solution, which are both part of the half cell. Or, if we're not going to be part of the half cell, then we need an inert electrode. These could be things such as platinum, in the case of the standard hydrogen electrode, or in the iron 2 plus, iron 3 plus electrode, or we could use a graphite carbon electrode like we see in the extraction of aluminium. Either of those electrodes do if we're not using a electrode which is part of the half cell. To connect the two electrodes together, we need to use a high resistance voltmeter, and we use a high resistance voltmeter in order that current doesn't flow in our circuit and that we get a true electropotential reading. Between the two solutions, or the two half cells, we need to complete the circuit by including a salt bridge. The standard solution that you use for the salt bridge is a potassium nitrate, and you normally just create this in class just by dipping in probably some filter paper, something like that, into a saturated potassium nitrate solution, connecting the two half cells together. Each of your electrodes needs to be dipped into the solution again. If they're not dipped into the solution, then they're not going to be part of the cell and you're not going to have a complete circuit. The standard conditions for creating and measuring the EMF of an electrochemical cell is 1 atmosphere. Your solution should be 1 mole per decimeter cubed and the temperature should be 298 Kelvin. The next practical activity then is to investigate how the pH changes when a weak acid reacts with a strong base and when a strong acid reacts with a weak base. We do this using normally a pH probe such as a pH meter, and we can see here we've got an example of a pH meter which is placed into a solution. Make sure these are washed before you put them in a solution and you take care of the ends. The key information that you're likely to look at this is the shape of the pH curves which are produced when you add an acid and a base together, and these have been seen in previous lecture on acids and bases in the titration curves, and there's a link to it just coming up now if you want to look at them in detail. There are a couple of things just quickly reminding ourselves. If we've got a pH curve here with a pH indicated on the y-axis with volume of substance added on the x, we're starting at a high pH going to a low pH, remembering here that you've got a strong alkali to start with and you're adding a strong acid. In the other case here, when we're looking at pH on the y-axis again and volume of substance added on the x, again, if you're starting at a low pH, you're starting with an acid, and to that you are adding a strong base. Otherwise, the rest of your pH curves you can pick up from the video tutorial on titration curves, the link below. Number 10 then is looking at the preparation of a pure organic solid and how we test its purity. Pure organic solids are formed quite easily, but organic solids are quite easily formed, but to purify them we have to do several steps. The first thing we would do is a recrystallization where we dissolve the solid in a minimum amount of hot solvent. We dissolve the solid in a minimum amount of hot solvent in order to saturate the solution with the crystal, with our organic product even. What this means is we might get a small amount of impurity dissolve in the solid, and also we'll get any impure solids that won't dissolve, which we can filter out by filtering the hot solution, leaving impurities behind in the filter paper. Once we've filtered it, we can leave the solution to cool. The cooling process will allow the pure solid to crystallize out, and we will be left with a liquid with some organic crystals inside. Once we've collected the organic crystals in a beaker, we can filter this substance and we can wash with a small amount of ice cold solvent, and we're using ice cold solvent, so only very small amounts of it will redissolve, and we will add drying agents. Well, we won't add drying agents, we'll simply put it somewhere warm to dry the crystals so that we can check the purity at a later date. Once we've left the crystals to dry, we can then test the purity of the crystals, and we test the purity of the crystals by doing a melting point check. And we do that by checking using melting point apparatus. There's 3 examples of melting point apparatus here, and they all work in a very similar way. Each of these devices, you compact your organic solid into a capillary tube, and then you place the capillary tube next to a thermometer against some heating block, heating mantle, or in the case of the one on the right hand side here, you put the capillary tube in with an oil which you heat up. You then gently warm the heating mantle or the oil, and so that the organic product or the organic crystal starts to warm up, and eventually the solid melts. Once the solid melts, you can compare the melting point with the data book value. So I've written warm there, and it should say with data book values. We have to heat slowly, because heating too fast can lead to heating past the melting point and ending up with inaccurate results, which is not of any use when we're trying to check for the melting point. If the organic product is pure, then we end up with a sharp melting point with a narrow melting point range. This is because it will crystallize evenly, and there won't be any interaction from other molecules disturbing the intermolecular forces. Finally then, in organic purification, we'll look at the pure preparation of a pure organic liquid. If we got an organic liquid, we can separate it out, and we can wash the organic product with water, and that will remove any of the water-soluble impurities which exist in our substance. We do this by mixing with water in something known as a separating funnel. The separating funnel is simply a device with a neck, see-through neck with a tap at the bottom. The tap at the bottom allows us to tap off different layers of either organic or aqueous substance, and normally we would have the aqueous layer sitting underneath an organic layer on the top. So once we now mix our organic layer with aqueous solution, remove the soluble impurities, we tap off the aqueous layer with the impurities, and then we add magnesium sulfate here finally as a drying agent to remove any excess water in our organic layer. Once we've got our organic layer, even if we still have impurities, our final option is then a distillation. So a distillation we've also seen in our previous lecture, a link to here if you want to go and see it, from practicals 1 through to 6, where we've seen the acidified potassium dichromate distilling to aldehydes, the primary alcohols, or the new practical technique here where we've seen separation funnel. Number 11 then is to carry out simple test tube reactions to identify transition metal ions in aqueous solutions. These are relatively straightforward practicals, and you've got to be aware how to pipette things such as sodium hydroxide or ammonia or sodium thiosulfate SCN, and you're looking at the dropwise addition of these samples to aqueous metal ion solutions. The products from these vary depending on the amount of sodium hydroxide that you add, the amount of ammonia that you add, and in some cases if you're adding sodium thiosulfate. The practicals themselves are pretty straightforward, but the key thing is then the observations that are made. You need to observe specific colours, and these are different for depending on the metal that you're using. Whether you've got a precipitate that forms when you add sodium hydroxide, and you know if a precipitate forms because you can no longer see through the solution, or whether you remain a solution. Perhaps you see a colour change, perhaps it goes from blue to green or green to yellow, but remains as a solution. You may notice that you've formed initially a precipitate, but then when that further addition of sodium hydroxide or ammonia, you add more, you say that it redissolves. The precipitate redissolves. Might be an observation, or the final observation might be that you add either sodium hydroxide, ammonia, etc., and that there's no change in the reaction, and we describe this by saying there's no visible change. Getting used to writing these as observations in experiments is important, and is presumably one of the aspects that the AQA exam board might be looking for you to recall in an exam. The only final thing is just to point out that we have the dropwise addition, and once we've added dropwise, we may then go on further, add more sodium hydroxide or ammonia, and the way that we describe this addition of more solution is to add to excess of sodium hydroxide or ammonia. The final practical activity then we've got to look at is the separation of species by thin layer chromatography, which I have looked at in the DNA section, but we'll look at once again. You need to be able to recall how to do the thin layer chromatography by spotting samples of sample onto a thin layer chromatography plate. A thin layer chromatography plate is usually something which has got a foil back, and then some sort of silica powder which is stuck to the front side, which allows solvents and samples to pass up through it. What we have is we generally have a pencil line at the bottom. We use pencil because that's not going to be soluble in any of our solvents. The solvent, we make sure that we dip our thin layer chromatography plate and ensure that the solvent is above the line of the pencil. Onto the pencil line, we spot our sample. So we try and put a concentrated spot of the sample onto the pencil line that we draw. Now, ideally, this picture is not drawn too well, but this is actually in a sealed vessel, the hole, and the reason we do it in a sealed vessel with a lid on is so that the solvent doesn't evaporate during the thin layer chromatography. We then do the thin layer chromatography by putting it in and leaving it for some time, and we wait for the solvent front to reach near the top. The solvent front is simply the distance moved by the solvent and is measured by this value y from the pencil line up to where the solvent stops. We then can identify how far the spots have moved over the experiment, and the distance each of the spots has moved we define as x in this example. The final thing that I should point out is that since we're using an organic crystal, we have to find some way of identifying the spots because they're probably invisible to the human eye, and we'll generally use either UV light to show up the spots, or we can use a locating agent such as ninhydrin. We need to choose one of these methods rather than both. Once we've identified and can see the spots, and we can actually get that value, that measure of x, so we can work out how far the species has actually moved. And we can start to calculate a value for this x over y, which we call the retention factor. This retention factor is unique for a given solvent and sample, and is sometimes also described as the RF value. Because the x value can never be greater than the value of y, it's always a value which is less than 1 and comes up as a decimal. We can compare our retention factor with data book values, and we'll find out that for given organic products and given solvents, they're unique. So at the end of this session then, you should now be able to recall the 6 additional practical techniques for AQA A-Level Chemistry Year 2. The Year 1 and Practicals 1 to 6 can be found via this link here. I hope you've enjoyed the video. Do like and subscribe for more. Thanks a lot for watching. I'll see you soon. Bye for now.